All right, so a quick recap. So this reaction quotient can be used to determine, not only if a system is equilibrated or not, but if it's not, which way it's going to um, react spontaneously to get back to an equilibrated state. So let's see if you can figure out the numbers. Now for each of these, if Q is smaller than K, larger than K, or equal to K, I want you to figure out if the system is going to be reacting spontaneously in the forward direction, in the reverse direction, or not at all. All right, so if Q is smaller than K, then that's going to indicate that it's A, not equilibrated, and B, going in the forward direction. If Q is larger than K, then you want to decrease the product concentrations, increase the reactant concentrations. So that is reverse. And last but not least, if it happens to equal K, then you're, of course, at equilibrium. Now, the other thing, just as a little preview here for an upcoming chapter, that Q will tell you is that how much work can be extracted by a system that is trying to get back to an equilibrated state. Next up, and last for the chapter, LeChateliers Principle. And this talks about what happens when an equilibrium is disturbed in a much more quantitative sense. If you look it up in a textbook, you will see something that looks like this. If a system is at equilibrium is disturbed by a change in temperature, pressure, or component concentration, the system will shift its equilibrium position as to counteract the effect of the disturbance. And these are the words of LeChatelier himself. And that is incredibly boring and probably doesn't mean anything to you. This is one of those things, one of these great universal truths. And I think something is a great universal truth if it was taught to you by one of two people. Number one, your mother, or number two, your kindergarten teacher. And in this case, at least for me, it was my mother, who, and I will paraphrase her a little bit. Actually, I will quote her, "Mais là comme c'était avant." So my family is Quebecois, so we get yelled at in French. The translation is put it back the way that it was, and this is what she would tell my brother or I when we disturbed the delicate equilibrium that was our household. But this is something that you already know. Actually, you know it even in greater detail because this is just Q in disguise. It is a qualitative version of Q. So let's review a little bit here. So we've got this generic reaction in equilibrium with products. And the thing is though, and what's beautiful about this is that to counteract a disturbance in equilibrium, to get back to a different equilibrium composition, there's really only two things a reacting system can do. It can go forwards or it can go backwards. That's it. And all you have to do is ask yourself which direction will counteract the change that was just imposed. So for example, if you add a reactant between reacting forward and reacting reverse, if you add reactant, the counteract to that is to convert them into products. So that's forward. And let's say if you add a product to an equilibrium mixture, then you want to get rid of it, which means that you will, by extension, form some of the reactants. You'll be reacting reverse. And so a couple of other things. You could, let's say, increase the pressure on a system. That was the other thing that was mentioned in the original definition. And the way that works out is that you're going to react spontaneously toward the direction that has the fewest number of gas moles, so that the overall pressure is reduced to the extent possible. And the only other thing we think about, so these two are by far the most common disturbances that we talk about. And the other one is you can also talk about heat, and that one is just simply the way that you figure that out is consider it to be a product if it's an exothermic reaction, heat's given off, and if it's an endothermic reaction, treat it as a reactant. And so I'm just going to go over a quick example, and you can figure to give you some practice with this. All right, so here's our example process. We have dinitrogen monoxide, laughing gas by the way, reacting with nitrogen dioxide to form 3 nitrogen monoxides. And you will note from the delta H here, that this is positive, meaning it's endothermic. And that is an important hint. All right, so I have 6, possible disturbances to an equilibrated mixture of N2O, NO2, and NO. And so there's a few ways that we discuss this change of the direction. We can say that it shifts towards the products or the reactants. Left and right is also another way that we often say it. So shifting to the right means shifting toward the products. Shifting toward the left means shifting toward the reactants. Again, this is why it's important to always write the reaction so you're aware of, to you, what's left and what's right. All right, so take a minute, think about all of these, and make it, encircle left, right, or no change, and come back and check your work. All right, so the addition of N2O. So in this case, you are adding a product. You want to react it away, which means that you're going to be shifting towards, you added a reactant. You want it to shift away, so that's going to be shifting it to the right. Now, you can add stuff. You can also take it out. And again, think about just which direction is going to counteract that change. So you removed one of the reactants, and you want to make some more to replace it, which means in this case you'll be shifting to the left for this reaction. And if you happen to add a product, in this case the one product, NO, the counter to that is to react it away, which means that will also be going left. You're going to react away some of that reactant and make some of the products in the course of that. Now, temperature. So I talked about this, and remember that the key to this is to treat heat as if it is explicitly a product or a reactant. Now, if it's endothermic, the way that you interpret that is if the system needs heat, it takes it in from the surroundings. So you could just say something like that. And then treat it, again, just as a reactant. And so if you increase the temperature, you're increasing the heat. That's the same thing as increasing one of the reactants, which means you'll react in the forward direction to counteract that. Decreasing the volume. So I didn't talk about volume in the previous slide, but I did talk about pressure. And for gaseous systems, or for any systems, those two are related. And so decreasing the volume. So in this case, this is going to mean increasing pressure. And what we said here was that we're going to shift in the direction that has the fewest overall number of gas moles. So in this case, you've got 3 moles of gas here and a total of 2 on this side. So you're going to shift toward the reactant side, which we're going to call left. And saving the best for last, what if I added a bunch of helium at constant volume? Now, what matters here, and think back to Kp, right? So adding the helium, so how are these last two different? Both of them are going to increase the pressure of the system, but this one, adding the helium, doesn't change the partial pressure of any of the components. You're adding something that is not involved in the equilibrium at all. So the end result here is no change. And if this is befuddling you, well, just construct the equilibrium constant expression for this system and look for the helium. So there is no helium concentration term. So changes involving a species that is not actually involved in the equilibrium has no effect on it. All right, so that is LeChateliers principle. Remember, it is just Q without the math, and that is the chapter.